Okay, this is section 5.3, and we're going to talk about something called a polynomial function. So we have kind of 5 basic things we want to accomplish. Number 1 is to just define what a polynomial is. Number 2, you want to talk about what does it mean to find the degree of a polynomial. How do you evaluate one? That means how do you plug in numbers to find what it should equal. What does it mean to say find the zero or the solution of a polynomial? And then finally, what's the end behavior of a polynomial, which means how does the graph look as it goes forever in either direction. Okay, so first of all, here's the definition. What is a polynomial? It's basically an expression that looks like this. It has x or some variable being raised to different powers, and usually there's a number in front of the x, like a coefficient. That's what all those a's mean. And then we call that coefficient, so you can see this table right here. We say, first of all, that a polynomial is written in standard form when the exponents are going in decreasing order. So for example, if you look at these right here, in all of them, like this third one right here, you have x cubed, x squared, x to the first, and even though there's no x here, that's really like x to the 0. That's written in standard form. The degree of a polynomial refers to the largest exponent. So this is the largest exponent, and that polynomial has degree 3. This polynomial right here, the quadratic, has degree 2, because the largest exponent there is 2. This linear equation, linear means x is being raised to the first power, so that has degree 1. The leading coefficient just means the number that's in front of that highest exponent term. So for example, in this cubic, 8x cubed, 8 would be the leading coefficient because that is in front of the x cubed term. In the quadratic, 5 would be the leading coefficient because that's in front of the largest exponent, the x squared term. And then if there is no x term at all, like this constant right here, 12 is both the leading coefficient and it's the only term there. So those are just some terms to be familiar with when you're talking about polynomials. And by the way, the word polynomial actually means this right here. Poly means many, and nomos refers to terms. So the terms are separated by plus and minus signs. Like this one right here, the cubic, has 4 terms. 8x cubed, minus 12x squared, 3x, and 1 would be the 4 terms there. So let's go through these and we'll state the degree and the leading coefficient of each polynomial in one variable. And it says if it's not a polynomial in one variable, explain why. Well, this one is not, because that has 2 variables, x and y. And then this one also is not a polynomial, and the reason is you're not allowed to have x's on the bottom of a fraction like that. In an earlier section we said x is raised to non-negative powers, and this you could actually write as 4x to the negative 1. X to the negative 1 means you flip it to the bottom and it becomes x to the positive 1. So neither of those other two are polynomials. The top ones though are. So this one, part A, has degree 5 because of that term right there. It has the largest exponent of 5, so degree 5. And the leading coefficient, I'll abbreviate that LC, leading coefficient there is 8, because 8 is the number in front of the highest exponent term. For this one right here, this is going to have degree, and it looks like, you might be tempted to say it has degree 4, but there's actually a term right here that has a higher degree, degree 8. So that's not written in standard form. The exponents are not descending, but that's still the highest degree. And then the leading coefficient is this entire thing. It's negative 4. Okay, it's the whole number in front of x to the a. So leading coefficient is negative 4. Those are both polynomials. Okay, so the third thing we want to talk about is how to evaluate polynomials. And how you evaluate is a fancy word for find the value. So all you need to do is just take the things that they're giving you and plug them into this equation. So this right here, this p of x, let me just rewrite that because it's a little bit blurry. Okay, this is saying this is a function, and this right here, p of negative 2, means wherever you see an x in this function, which I see right there and there, wherever I see an x, I should now replace it or plug in or substitute the number negative 2. So we'll do that. Negative 2 to the third power is negative 2 times negative 2 times negative 2. That's negative 8. Negative 2 to the fifth power is negative 2 times itself 5 times, and that turns out to be negative 32. And then minus a negative 32, that's like plus 32. So negative 8 plus 32 turns out to be positive 24, and that's the answer. Okay, the second one says p of 3 Same exact procedure, only difference is instead of plugging in -2, we will plug in +3 wherever I see an x. So here and here are going to get 3 plugged in. 3 to the third minus 3 to the fifth. Let me divide that. So 3 to the third power 3 times 3 times 3 is 27. 3 to the fifth power 3 times itself 5 times is 243. 27 minus 243 would be -216, and that's all you need to do, just plug it in. Okay, notice that there's nothing we're doing on the left side. P is not a variable. It's not like we're trying to solve for P. This is a faster way of saying this. P of 3 is just a shorthand way of saying plug in 3 wherever you see an x. That's what that means. Okay, this one on the right, a little bit trickier. Now we're not plugging in numbers this time, we're plugging in variables, but it's still the same idea. So f of x is this right here, this function. And they're asking us to do two things. So let's start by finding this, and we'll start by finding this separately. So f of 3c minus 4, actually do that in a different color here, just to make it clear what we're doing. So here's what this means. F of 3c minus 4, that means wherever I see an x, so I see an x here and here, I'm going to plug in 3c minus 4. So those parentheses that used to be empty, that's where the x's were. And they're telling me plug in 3c minus 4. So this one right here, 3c minus 4 squared, means this. Plus, okay, 2 times this when I distribute is going to be 6c minus 8. This right here, when you FOIL it, 3c times 3c is 9c squared. 3c times minus 4, that's minus 12c. The inside terms will be minus another 12c. And then minus 4 times minus 4 is 16. And we have to include these terms that we had before. When we combine all of these like terms, we have 9c squared. We have minus 12c, that's minus 24c, plus 6c would be minus 18c. And then we have 16 minus 8 is 8. 8 minus 3 would be positive 5. So now we have at least part of our answer. And I'm going to write that right up here. So this right here, let me give us a little bit more space here. This right here is equal to 9c squared minus 18c plus 5. That's the first part. Okay, now we have to find f of c, and that's a little bit easier actually. Let's use a different color here. So f of c just means wherever you see an x, you're going to plug in a c. Actually, let me change the color there. So wherever I see an x, I'm going to plug in a c. Well, I see an x here and here where those empty parentheses are. So I'll plug in a c. Then when we simplify this, c squared is just c squared plus 2c minus 3. But notice they're asking us for 5c. So I have to multiply 5 times f of c. I have to multiply this thing right here by 5 to get my final result. So 5 times this thing just means we distribute the 5, and we'll get 5c squared plus 10c minus 15. And now here's just one thing to notice. So that's 5 times f of c. But notice that it says minus 5 times f of c right here. So I'm going to substitute this in exactly like it says. That was our first part. We have a minus, so there's a minus. And then 5 times f of c was this thing down here that we had. So that's going to go right here. So 5c squared plus 10c minus 15. The reason I put the minus in front of a parentheses like that is because this will now distribute, and it's going to change all the signs in here. So the first part is still 9c squared minus 18c plus 5. When you distribute this minus, you get minus 5c squared minus 10c, and then minus that negative 15, that becomes plus 15. Last thing we need to do is just combine the like terms. So we have, these like terms, we have 9c squared minus 5c squared, that's 4c squared. Next like terms, we have minus 18c minus 10c, that's minus 28c. Last like terms, we have plus 5 plus 15, which is plus 20, and that's the final answer. That was quite a bit of work, but just to recap what we did, the main steps here are to calculate this thing and this thing individually by plugging in what's in the parentheses for x right here. And then you simplify it at the end by subtracting those two things. Okay, one of the last things we're going to talk about in this section is the graphing polynomial functions, and it's a good idea to know the basic shape of each polynomial. Okay? And then there's a rule about how many, so you might see with these polynomials, a lot of them, they turn, they kind of have these turns. So this is the basic graph of x to the first power. That's just y equals x, or mx plus b, slope-intercept form. This one is the basic graph of a quadratic function, and the maximum number of turns that a quadratic, so that means x to the second power, so this might be like negative x squared plus 2 or something like that. The maximum number of turns is going to be 1. So here's the turn right here. It's going up, and then it suddenly turns to going down. And in just a sec, you'll probably be able to see a pattern. Cubic function is on the bottom left side, so this is like x cubed, and you can see it has, just change the color so it's a little bit clearer, it has a turn right there, and it has another turn right there, so that has 2 turns. It's being raised to the third power, but it turns twice. This one is quartic, it has 1, there's a second turn right there, and there's a third turn right there, so it has 3 turns. It's being raised to the 4th power, it turns 3 times. And this last one has 1 turn there, second turn there, third there, and a 4th there. So it's being raised to the 5th power. It has 4 turns. So what this means is that whatever degree, whatever power the function is raised to, it can turn 1 less than that amount of times. Being raised to the 2nd power, it could turn a maximum of 1 time. Being raised to the 3rd power, it could turn a maximum of 2 times. 4th power could turn at most 3 times. 5th power could turn at most 4 times. Okay, so that's useful to know. And then when it comes to the shape of a graph, there's really only 2 that you need to know to be able to answer this question about end behavior. So here's the only 2 graphs that you really need to know what they look like. If you know what these look like, you'll know what every other graph looks like when it comes at least to polynomials. So here's what the graph of y equals x squared looks like. It's a U shape, it's a parabola. And here's what the graph of x cubed looks like. The right half starts out like a parabola, so it's kind of like that, but then the downside right here goes down. So what does this stuff mean when they're talking about end behavior? Here's what it means. As the graph is going this way, okay, notice that we're traveling, not only are we going up, but we're also going to the right direction. This line right here is drifting, you follow it, it's drifting to the right. So x is 0 here, 1, 2, 3, 4. This graph is going more and more in the x direction. And eventually, if you were to follow this graph, if you kept it going forever in that direction, well, x would go forever. And how do you say forever as a number? You say infinity. In which type of infinity is it going towards? Well, these are positive numbers. That's a 1, 2, 3, 4. So x is going to positive infinity in that direction. Okay, other side of the graph, as we're going this way, well, here's x is 0, negative 1, negative 2, negative 3. When x is still traveling in this direction it's traveling towards infinity in the negative. So that's the symbol right there. That like sideways 8 is the symbol for infinity. Same thing over here on the cubic. So here in this direction, x is going to infinity in the positive direction. In this direction right here. Okay, now again, I know it looks like the graph is going down, and it is, but we're just focused on which direction is moving in the x, and x is in this direction, is drifting towards the left, so it's going to negative infinity. If you follow this and you kind of pay attention to these numbers here, it's going negative 2, negative 3, negative 4. If you kept following it, it's just going to keep going more and more to the left. So that is kind of the shape of the graph. Now, what does end behavior mean? End behavior means where does the graph end up? That's why it's called end behavior. How does the graph end up behaving in terms of its y value as you go further to the left or the right? So if you look at this parabola, as x goes to positive infinity, f of x, which is the same as y, f of x is going upwards forever. So f of x is going to positive infinity as well. And this is what this means right here. That means f of x, arrow means, is traveling towards infinity in the positive direction. Same thing right here. On this side, as x goes to negative infinity, this arrow, this green arrow, the y value, or the f of x value, is still going to positive infinity. So here's the thing, if you know what x squared looks like, you know what every even-numbered graph looks like. So that end behavior that we just talked about there, that's also the end behavior for x to the 4th, for x to the 6th, for x to the 8th, for x to the 182nd. Every single graph that ends in an even power will look exactly like x squared in terms of its end behavior. It's not going to look the same necessarily in the middle, but it will always end up in the same place. Okay, if I were to put a negative in front of it, so suppose I graphed y equals negative x squared, all that does is it takes the parabola and it just changes that to make it go upside down. So how does that change the end behavior? As x goes to positive infinity now, this arrow right here is the f of x. That's going downwards. That's going towards negative infinity. Here on the other side, as x goes to negative infinity, where is this arrow going? It's going to also to negative infinity. So that's the thing to know. With even numbered exponents, the f of x always ends up in the same place, either positive or negative infinity. Okay, how about this one right here? So as the cubic function goes, as x goes this way, f of x goes up towards positive infinity. As x goes this way, down here, f of x goes towards negative infinity. So the x's and the y's go the same directions on odd numbered polynomials. So if you know x cubed, you also know what x to the 5th looks like, x to the 7th, x to the 9th, x to the 175th. Every single odd numbered exponent looks like that. Okay, what if you put a negative in front of it? So let's say we graph y equals negative x cubed. That just takes this part on the right and it flips it over. And it takes this part on the left and flips it over. So now this end behavior right here, as x goes towards positive infinity, the y function, the y value right here, is going down towards negative infinity. On the left side, as x goes towards negative infinity, because we're in the negative region of the graph right here, where's f of x going, you can see this arrow is pointing upwards towards positive infinity. So if you know what x squared looks like and you know what x cubed looks like, you know every other even or odd number. Here's another thing to note in terms of the number of zeros. 0 means how many times does it cross the x-axis. Okay, all you need to do basically is look at whether it's an odd or an even number, and that will tell you the types of zeros. So odd degree functions like this stuff right here. Okay, this is something like x to the 3rd or x to the 5th. That has an odd number of zeros. There's 1, 2, 3 zeros. 3 is an odd number. So odd degrees will always have an odd number of zeros. There's 1, 0. 1 is an odd number. Even degree functions, like for example, this might be x to the 4th right here, that has 1, 2, 3, 4 zeros. 4 is an even number. And then the same thing right here, you have this never touching the x-axis here, so it has no zeros. In this case, no zeros are considered, in a sense, they're considered like an even number. Okay. Now here's one apparent exception to that. Suppose I graphed x plus 3 squared. That's a parabola. X plus 3 squared, the graph of it looks like this. That looks like, we just said that something with an even degree is supposed to have an even number of zeros. That looks like it only has 1 zero. So what's the catch? And the catch is x plus 3 squared can be written like this. And it has this 0, x equals negative 3, but this 0 is like being counted as though it were a double 0. It's counted twice. So that still fulfills the rule. You're just counting negative 3. You're kind of double counting, so it still fits with that pattern. Alright, last thing we want to do is for each graph we're going to describe the end behavior, tell if it's odd or even degree, and have the number of real zeros. So let's do the last one first. The number of zeros is the easiest to find. This one, let's see how many zeros it has. It has 1 0 there, it has another 0 there. It has 2 zeros. 2 is an even number, so it must be an even degree. And then the end behavior, well, as x is going towards positive infinity right here, because that's where it's going on the right half of the graph, the function is going down. This arrow is pointing down forever. That means down to negative infinity. Over here, as x is going to negative infinity, because we're on the left side of the graph where x is negative, the function is still going down. That means it's still going to negative infinity. That arrow is pointing down. That's probably something like x to the 4th power or x to the 6th power, and it's going to be a negative. Okay, so it could be anything like that. We're not sure, but we know it's negative because it's flipped over from a normal looking parabola or a normal parabola-like shape. Okay, the next one, the last one, is an odd degree. So there's 1, 2, 3, 4, there's 5 zeros. Since 5 is an odd number, that means it's an odd degree. So it might be something like, well, if it turns, notice it turns 1, 2, 3, 4 times. So it could be anything like negative x to the 5th, negative x to the 7th, and so on. The reason I know it's negative is because the normal third degree function looks like this, where this side of the graph is going up, and on here it's going down. So as x goes to positive infinity, you can look at that arrow right here. It's going down forever. That's going to negative infinity. As x goes to positive infinity, or sorry, as x goes to negative infinity right here, that arrow, or the f of x, is pointing up towards positive infinity. So that is what we mean by end behavior, and that's section 5.3.